Alright, section 5.2 is the addition rule and the rule of complements. In this section we're going to be using the definition of probabilities that we got last time in section 5.1. Remember we said that if I asked you to find the probability of A, what you would do for the theoretical probability is look at the number of elements in A divided by the number of elements in your sample space. Remember, your sample space is the collection of all possible outcomes for an event, whatever that event may be. We're going to be using this basic probability tonight, but we're going to be kind of introducing some things that are a little more complex to go with it. There's 3 objectives for tonight. We're going to look at probabilities using the general addition rule, also using the addition rule if we have 2 things that are mutually exclusive, and then look at the rule of complements. Objective 1 is to compute probabilities by using the general addition rule. I'm going to introduce this rule using something that's called a Venn diagram. The general addition rule is used whenever you are trying to find the probability of 2 events when those 2 events are separated by the word or, the probability of A or B. I'm going to let this circle represent the events or the elements that are in event A, and I'm going to let this circle represent the elements that are in event B. The rectangle here represents my sample space, which is all possible outcomes. So I may have things out here that are in the sample space, but they're not in either A or B. Now I can represent the probability of A by shading everything inside the circle that belongs to A. And I can represent the probability of B by shading everything that's inside this circle that belongs to B. If I want to find the probability of the compound event, the probability of A or B, I could add the probability of A to the probability of B, but the probability of A here is equal to everything that was inside this circle right there. The probability of B, I said, was everything inside of this circle that looks like this. If I were to just add these 2 probabilities together, do you see a problem here where these 2 circles overlap? I've counted that region twice, haven't I? What we do then to take away so that I only count this region once is I need to take away the probability of A and B happening at the same time. That overlap is represented by this region right here where I've overlapped those probabilities. Because this area of overlap happened twice, I want to take it away once. Does that make sense why I would want to take that away? Alright, so the probability of A would be this region, the probability of B would be this region that's represented by the circle for B, and then where things overlap, then I'm looking at the A and B happening at the same time. This region of A over here where there is no B, that's just A happening by itself without B. This region over here is B happening by itself without A. But this region right here is where both A and B happen, whatever A and B happen to be. That's how we get this general addition rule. A compound event is an event that is formed by combining 2 or more events. One type of compound event is of the form A or B. The event A or B occurs whenever A occurs, B occurs, or both A and B occur at the same time. Probabilities of events in the form A or B are computed using the general addition rule. In this example, we're going to look at the general addition rule. I'm going to go through the process of solving this problem the first time by using this rule, and then the second time I go through the process of solving it, I'm going to show you how to solve it using common sense. Since we're going to be using the general addition rule, I'm going to begin by writing that rule down again. In this example, we're told that we have 1,000 adults who were asked whether they favored a law that would provide support for higher education. In addition, each person was classified as to whether or not they would be likely to vote or not likely to vote based on whether they voted in the last election. What is the probability that a randomly selected adult is likely to vote or favors the law? Let's begin by writing down what our 2 sets here are. A is going to be the set of people who are likely to vote. B is going to be the set of people that favor the law. Now remember, I told you the probability of any event is going to be equal to the number of elements in the event divided by the number of elements in the sample space. Since I'm finding probabilities here, I'm also going to identify how many elements are in A and B and my sample space. The number of elements in A The people that are likely to vote, the way I read this table is I go across and everybody that's in this row right here represent the total people that are likely to vote. So to find the total number of people that are likely to vote, I would add 372 plus 262 plus 87, and that's going to give me how many? Then to find the number of people that are in set B, I look at all of the people who favor the law. That's going to be 372 plus 151. And that's going to be how many? 523. In this formula, I need to also identify what A and B are. A and B are people who are likely to vote and favor the law. To find the people that are likely to vote and favor the law, this represents the people that are likely to vote. This column represents the people who favor the law. Where is the intersection? Those represent the people that are going to do both. These are the people that are likely to vote and favor the law. So how many elements are in both A and B? Just 372, because that's where these two columns intersect. The other thing that I need to know is the number of elements in my sample space so that I can calculate this probability. How many elements are in our sample space? We have 1,000 adults who were surveyed. Our sample space is all of the 1,000 adults, so the number of elements in our sample space is going to be 1,000. Just using this formula to find the probability that a randomly selected person either favors the law or is likely to vote will be found using this formula, because I use the word or. So to find this probability, I need to find the probability of A, which is the number of elements in A divided by the number of elements in the sample space, plus the probability of B, which is the number of elements in B divided by the number of elements in the sample space, minus the probability of A and B, which is the number of elements in A and B at the same time, divided by the number of elements in our sample space. I have all of these components identified over here in gray. So this first number is going to be 721 divided by 1,000 plus 523 divided by 1,000 minus 372 divided by 1,000. When I put this into my calculator, I get a total of 0.872. So we found the probability that a randomly selected person is either likely to vote or favors the law. I told you I could also show you how to do this using common sense. Are you ready for the common sense? You identify on this table all of the people that are likely to vote or favor the law. That's these four numbers right here. That's all you do is you add those numbers up and then divide that by 1,000. If you add all four of these numbers up, you end up with 872. And 872 divided by 1,000 is 0.872. So using common sense, I would say the probability of A or B is equal to 372 plus 262 plus 87 plus 151 divided by 1,000, and that's equal to 0.872. Both methods work. I don't care which one you use. Common sense one works every time. You can only use the common sense one though if your information is organized in like this in what we call a contingency table. Personally, I like the common sense one, but it's important that you understand how the general addition rule works. For me, I think it's easier to understand the general addition rule if I use this picture that I gave you of the Venn diagram, because the part that seems strange to me is why are we subtracting this probability of A and B? It makes sense to me. If I want to know what's the probability of A or B, I would just add those probabilities together. But when I draw the picture, I see that if I have events in common between A and B, those events got counted twice. So I have to take them away one time. This method was using the formula, and this method using common sense. And I don't care which method you use. And here it is all written out and typed up all pretty for you if you want it. This is in the notes. Everything that's on the screen in print is already in the notes. The only thing that's not is anything that I handwrite. Objective 2 tells us how to find probability of A or B if our two events are mutually exclusive. Mutually exclusive just means that there's no overlap or no common element between the two groups. Looking at the Venn diagram, this Venn diagram represents two groups, A and B, that are mutually exclusive. This picture, just like the one that I drew before, are not mutually exclusive because I have elements that are in common right here. This region right here is why these two sets, A and B, are not mutually exclusive. In this example, I want you to identify whether or not the two things that are mentioned are mutually exclusive or not. In this first example, we're told that a die is rolled. Event A is that the die comes up a 3. So event A would just consist of rolling a 3. Event B, on the other hand, is that I roll an even number. Event B would be 2, 4, 6. The number of elements in A is equal to 1, and the number of elements in B is equal to 3. Just for giggles, what's our sample space? Our sample space would be all 6 numbers on the die, so the number of elements in B would be equal to 6. If I asked you to find the probability of these mutually exclusive events, what you would do is say, well, the probability of A or B would be equal to the probability of A plus the probability of B, because from our general addition rule, we have this. If our two events are mutually exclusive, the probability of A and B is going to be 0. It's impossible. Remember, the probability of an impossible event is 0. So to find this probability, all I would have to do is take the number of elements in A divided by the number of elements in my sample space plus the number of elements in B divided by the number of elements in my sample space. And that's going to be equal to 1/6 plus 3/6, and that total is 4/6, but we want to reduce our fraction, and that means that the probability of either rolling a 3 or rolling an even number would be 2/3. On the second part of this question, we're told that a fair coin is tossed 2 times. I have one coin, I'm tossing it 2 times. Event A is that one of the tosses is a head. If I'm tossing a coin 2 times and I need one of the tosses to be a head, I could toss a head and then a tail, or I could toss a tail and then a head, or I could toss 2 heads, couldn't I? When I toss a coin 2 times, all 3 of these give me the event that I have at least one head. Event B is that one of the tosses is a tail. Here I could have a tail first, then a head, or a head first and then a tail, or I could have 2 tails. Just for giggles, what's our sample space? It's every possible outcome, right? There's 4 different combinations of heads and tails I could get if I'm tossing a coin 2 times. Are A and B mutually exclusive events? There's a head tail, there's a head tail, there's a tail head, there's a tail head. They share things in common. These are not mutually exclusive events. A and B consists of head tail, tail head. If I asked you to find the probability of this scenario, you would have to use the general addition rule, and that would be equal to the probability of A plus the probability of B minus the probability of A and B. How many elements are in A? 3. How many elements are in B? 3. How many elements are in my sample space? 4. And how many elements are in A and B? 2. So to find the probability of A or B here, I would take the number of elements in A divided by the number of elements in my sample space plus the number of elements in B divided by the number of elements in my sample space minus the number of elements in both A and B divided by the number of elements in my sample space. Dropping numbers into this, then I would have 3/4 plus 3/4 minus 2/4. 3/4 plus 3/4 is 6/4. 6/4 minus 2/4 is 4/4, and 4/4 reduces to 1. Well, isn't the probability of our sample space 1? Let's think about this. If A is getting at least one head and B is getting at least one tail, either A or B is going to be a probability of 1. This or right here for the probability of A or B, it means either A happens or B happens or both happen. That's called an inclusive or. If there's no overlap, our events are mutually exclusive, and to find the probability of A or B, I just add the probability of A to the probability of B. If there is overlap between A and B, they're not mutually exclusive events, and to find the probability of A or B, I would find the probability of A plus the probability of B minus the probability of the overlap, or the intersection of A and B. And I've already given you now the addition rule for mutually exclusive events. You just add the probability of A to the probability of B. You don't have to worry about this part of the rule because this is equal to 0, so we just don't write it down. Here's an example problem that has us use the addition rule for two mutually exclusive events. In the 2012 Olympic Games, a total of 10,735 athletes participated. Of these, 530 represented the United States, 277 represented Canada, and 102 represented Mexico. What is the probability that an Olympic athlete chosen at random represents the U.S. or Canada? So let's let event A be the athlete is from the U.S. and B will be that the athlete is from Canada. How many athletes participated in the 2012 Olympics from the United States? And how many participated in the Olympics in 2012 from Canada? 277. And how many elements are in our sample space, or what is our sample space? It's all 10,735 athletes that participated in the Olympics. In reality, we do have people that have dual citizenships that are both a citizen of the U.S. and of Canada. But Olympic rules state that you can only represent one of the countries if you have dual citizenship. You have to pick one. So there won't be any overlap. That's why these two things are mutually exclusive, because you can't represent two different countries at the same time. You got to pick one if you have dual citizenship. And because these events are mutually exclusive, we would say the probability of A or B is just equal to the probability of A plus the probability of B. So that's going to be the number of elements in A divided by the number of elements in our sample space, plus the number of elements in B divided by the number of elements in our sample space. And that's going to be 530 divided by 10,735 plus 277 divided by 10,735. Give me an answer rounded to 3 decimal places, can you? So there's about a 7.5% chance that a randomly selected athlete will be from either the U.S. or Canada. Finding the probabilities of two mutually exclusive events, either A or B, is pretty straightforward. It's when they're not mutually exclusive that you have to stop and think about it. The last objective of this section tonight is probably the most confusing of the three. Objective 3 is to compute probabilities by using the rule of complements. I'm going to use a Venn diagram again to explain what a complement is. Remember, with the Venn diagram, the rectangle represents our sample space, and then inside it I've got something that I'm calling A. That circle there represents A. A complement, and I use a superscript C to represent the complement. A complement is everything in the sample space that's not in A. So if I tell you that there's a 60% chance of rain today, my event would be raining. What's the chance of no rain? 40%. Because rain and no rain are your only two choices. So if this is rain and there's 60%, no rain would be outside of that, and there would be 1 minus 0.6 would be 0.4. So if A is an event, the complement of A is the event that A does not occur. In this example, we're told that we have 200 students who were enrolled in a statistics class. We want to find the complements of the following events. Our event is exactly 50 of the students are business majors. If I have 200 students in a class, this string of numbers here represents the number of business majors. I could have anywhere from 0 to 200 business majors. The probability that exactly 50 of them are business majors is what we're going to call our event A. The complement of A would be that the number of business majors is not 50. My event here would be this number right there in this number line. Everything outside of that would be a complement. The next statement then is that more than 50 of the students are business majors. That's my event. The question then is, what is a complement? How would I write that out in words? If I'm using red to denote my event, more than 50, do I include the 50? So I'm going to say this group right here would be A. Would you agree with that? A complement then would be this group down here. How could I express that group in words? 50 or business majors? The question was, whenever you encounter these types of problems, am I going to want it written out in word form? You need to know how to write them out in word form, yes. Do you need to know how to calculate the number? Yes, you need to know that as well. Matter of fact, if I was looking at the number of elements in A here, that would be equal to 1, and then the number of elements in A complement would be 200 because I've got the 0 included there. On this one, the number of elements in A would be equal to 150, and the number of elements in A complement would be 51. Because I'm including the 0 here, that means that I've got 50 plus the 0 gives me 51. In this third statement, we're told at least 50 of them are business majors. That is now A. I've got to figure out how to express a complement. My event is at least 50 of them are business majors. Do I want to include the 50 now? When I say at least, if I told you I need at least $100, would I accept $100? Yeah, because that's at least $100. So when I say at least 50 of them are business majors, now I include this here, and that would be A. A complement would be this region down here. And how I would express that in words is I could say less than 50 business majors. For this scenario, how many elements would be in A? And how many would be in A complement? This would be 150 plus 1 is 151. Do you see where the plus 1 comes in? I've got 1 to 200, or 51 to 200. See, from 51 to 200 we had 150. If I did 200 minus 51, that would give me 149, plus the 1 for the 51 gives me 150. If I counted all the numbers here from 50 to 200, that's 150 plus the 50 where I started. That's 151. The number of elements in A complement would be from 0 to 49 is a total of 50 numbers. See, there's a grand total of 201 numbers because I'm including 0 as a number. These two numbers added together, which represents my sample space, have to total up to 201. 151 plus 50 is 201. 150 plus 51 was 201. 200 plus 1 is 201. You've got to pay attention. If it says more than 50, you need to know that more than something means you don't include that thing. If you say less than, you don't include that thing. But if I say at least or at most, you do include that number. So do you feel like you have a little bit of a feel of what the complement is? I'm going to go back to the Venn diagram that I drew earlier. I told you in this Venn diagram that the rectangle represents the sample space. Inside that sample space, I have A and I have A complement. The probability of A plus the probability of the complement of A has to be equal to the probability of our sample space. And how did we find probabilities? We said we'd look at the number of elements in something divided by the number of elements in the sample space. Well, that ends up being the number of elements in the sample space divided by the number of elements in the sample space over here. If I have the same number in the top and the bottom, what is that going to reduce to? 1. It reduces to 1. That leads me to this statement. The probability of A plus the probability of A complement has got to be equal to 1. Now, I could solve this equation for the probability of A by simply subtracting this A complement, probability of A complement, from both sides of the equation. And that's where I get the rule of complements, which says basically that the probability of an event is going to be equal to 1 minus the probability of the complement of the event, or the probability of the complement of an event can be found by doing 1 minus the probability of an event. Do you see how I take this rule right here, which comes from the fact that our sample space is either A and A is going to be made up of A and A complement, and I can apply probabilities to it and then find this rule of complements. You may be asking yourself, why do I even want to know this? Yeah, I can see that it's true, but why do I want to know it? And the answer is because of things that we have coming up in the future. Sometimes it's almost impossible to identify what an event is, your event A, but I can find the probability of the complement. I would use this formula to find the probability of my event once I knew what the probability of the complement of the event was. We use this rule of complements to find the probability of something if it's easier to find the probability of the complement than it is to find the probability of the event. Here's an example problem where we can use the rule of complements. According to the Wall Street Journal, 40% of cars sold in July 2013 were small cars. What is the probability that a randomly chosen car sold in July of 2013 is not a small car? Our event is that we have a small car. The complement would be not a small car. We were told in the problem that the probability that we have a small car is 0.4. Probability is 0.4. The percentage of cars that were small was 40%, but writing 40% as a probability, I changed that number to a decimal. The probability of the complement is going to be equal to, using this formula, the probability that it's not a small car is the probability of the complement of our event, and that can be found using 1 minus the probability of the event, but that's going to be 1 minus 0.4, and 1 minus 0.4 is 0.6. So 60% of the cars were not small cars. Question was, can you just use the common sense method here? And the answer is yes. But remember, I'm using an oversimplified example to introduce a concept that's actually quite complicated. So that's why I'm going through this process of showing you this. Next time the problems are going to get more difficult and I'm going to use this concept. So we've gone over how to use the general addition rule, how to use it if the events are mutually exclusive. We've looked at calculating probabilities of mutually exclusive events. We've talked about what the complement of an event is, and then we've looked at the rule of complements. Do y'all have any questions? No questions. We're going to stop this video.